My pleasure to turn today's program over to Dr. Christopher Barrett, President of 3D Directions. Sir, the floor is yours.
Thank you very much, Nora. Welcome, everyone, to Lecture 2, Laser Powder Bed Fusion. I hope this one is going to be a little more of a deep dive instead of the last lecture, which we had to kind of broadly touch on a variety of areas. So I'm really looking forward to this, and please mark down your questions. I definitely have time reserved at the end of this lecture for questions, and we'll try to get through as many as we can. So today's agenda, we're going to start with just a brief introduction to what laser powder bed fusion is. We will discuss some of the common defects. We're going to go over choosing the right parts, and then a brief question and answer period. So specifically for, if you remember the 7 types of additive manufacturing, we're dealing with the powder bed fusion category. We're going to deal today almost primarily with metals. Plastics are in the powder bed fusion realm with lasers, so it is under the subset of laser powder bed fusion. The differences between those is we typically have a heated chamber, and you're dealing with the glass transition temperature of the plastic, and you're only using the laser to tip it over the edge and not fully melt the part. Because of that, you have a variety of advantages to metals and the fact that you don't need supports. And it's a great thing, but we're not going to focus on that since most of the manufacturing sector is really interested in metals. We're going to primarily deep dive that. There will be crossovers. So in powder bed fusion for metal, there is laser and then there is electron beam. Electron beam melting is typically done in a vacuum. The electron beam will also partially fuse all of the powder. And because of that, you do not need the same support structures that you need in laser powder bed fusion, where we don't typically heat the chamber, and you are using the laser to fully heat the metal up to melt temperature and back down, so you're welding. Electron beam typically has a rougher surface on the hull than laser powder bed fusion. The electron beam, a lot of people are using that for your same lattice structures that you're doing with laser powder bed fusion, but if you need that surface finish, you typically need to go with the laser powder bed fusion side. They both have their quirks, they both have their uses. Depending on what type of manufacturing you're doing, you might want to go with the electron beam route to kind of delve through the nuance of the differences beyond what we're going to go through today. But certainly if you have questions about that, you can reach out to me after the meeting. My information will be on the last slide. So we're going to discuss the kind of the intro to laser powder bed fusion. This is a layer by layer laser welding process. So all of the physics that is involved with welding still applies in this realm. Typical tolerances that we can achieve, you can get, for small parts, you can hit a 20 to 100 micron features. Your minimal wall thickness that you can make is typically 0.3 to 0.4 millimeters. Surface roughness, 13 to greater than 100 micron RA. Density, most of these machines, actually pretty much every commercial machine you can buy can make 99% plus dense parts. Usually the issues come if the machine is out of spec or if you're using something on your own. You're developing your own powder, you're developing your own laser parameter, something like that, then you'll have to worry about that. But if you're doing what you're told, you should be getting good quality parts across the board. So if you're wondering which machines are just lemons and which ones are great, the answer really is in the nuance. It's not this one is complete trash. If you do what you're supposed to, you should be getting good parts. Standards are still being developed for these machines. Typically, the focus is to treat each machine like a mini foundry. So you're going to treat it like you're using one type of metal or only a couple types of metal. You're certifying that powder on that machine that you're getting good with those laser parameters and getting all those details worked out. There's a lot of things that affect this. Humidity If you are out west in the desert in a dry climate, you typically don't have as many issues with humidity. If you are in the northwest, where I am located, in the spring, we're running dehumidifiers nonstop just to keep the room climate controlled as best as possible, not to mention desiccant bags and the powder and all that. But if you, overall, if you're doing what you're supposed to, you should be getting close to these tolerances. Layer thickness and the different things you will do depending on your build will affect these. So when I say 20 to 100 microns features in small parts, to hit the 20 microns, I need to be doing really small layer thicknesses with really precise laser settings. Usually means I'm going slow, so my builds are taking significantly longer. So there is a balance here where you don't want to go too long. But overall, these are kind of average for what we see out there. Surface roughness is also dependent on if it's a side or a top or a bottom skin, and we'll go through that more. So some of the mechanics, we have a recoater. We obviously have a laser. Your laser is going to spot weld the layer. Your recoater is going to spread some of your powder supply onto the build plate and over to the overflow, and then go back and restart. Layer thicknesses are 20 to 200 microns. Most of the machines use a continuous wave laser, typically around 1064 nanometers. It's a GAG. Renishaw and some other machines do use a pulsed laser. And so we're going to go through most of all the laser parameters, assuming a continuous wave laser, but there is direct correlations with the pulsed. Both, again, are giving you great parts. There was a lot of debate back in the day as to which one's better, and there's still people who debate which one's better. And really, it comes back to if you're doing what you're supposed to be doing, you should be getting good parts. If something is not giving you good parts, there's a problem. Recoders can go in one direction. They can go back and forth in a bidirectional pattern. If that's the case, you would have your overflows on the outside, and both of those would be supply hoppers. You can have hard ceramic recoder blades, metal blades, soft silicone blades, wire brushes, rollers. Most of them are very good. There is nuance depending on what type of material you are using. Some of the materials are better with certain blades than others. And it kind of depends on what you're doing. Also, your recoder speed will need to change depending on what material and what type of blade you have. And if you're using a roller, there's still details. And there's pros and cons to all. Some of the defects you see with the hard recoder blades, and we'll go through this, where they'll actually gouge your part if the part is breaking. The soft recoder blades will give, but then you usually take a chunk out of the recoder blade and that propagates the part going up through. Wire brushes aren't as smooth, and rollers will usually pack the powder a little bit, which has its benefit as well, but also a con in the fact that you can crunch your part. And if you're building a small thin feature, that can break. So there's pros and cons with all of them. Really, if you have your machine honed in, you should be doing well. The chamber is usually inerted with argon. Sometimes we'll use nitrogen. There's a lot of machines now that are coming with a nitrogen onboard nitrogen generator. That depends obviously on what material you're working with, because you may need to make sure that since you're welding a metal, if it's in a nitrogen environment, sometimes it can react negatively and form a nitride with that metal, and that's obviously bad. Argon is pretty much the standard that most people will use. It's assumed you're using argon unless you can get away with nitrogen. So some of the laser parameters that we'll typically work with, you have your adjustable ones that we adjust for every build, every material type, every layer thickness, and then you have your set machine parameters. So your adjustable ones are your layer thickness. It's typically somewhere between 30 and 60 microns is normal, but I've seen anywhere between 20 and 200. Your laser power, again, that can vary between 100 and 450 watts is typically the high end that I've seen. It really depends on your scanning speed. So if you're moving faster across there, then you need a higher laser power to account for that, or if you're going slower. And then your hatch spacing. Your hatch spacing is largely dictated by your laser spot size and, again, your speed. Because if you're going slower, the melt pool propagates out a little bit. You can cover more area. But you need to make sure you have overlap. And then finally, your recoder speed, you kind of adjust for your machine. Your argon recirculation is set for your machine. Its direction is typically set. Its velocity, or its flow is set. And the laser spot size is set. So the advantage of the argon recirculation is, since we're already filtering the chamber and keeping the chamber inert, we monitor the oxygen level pretty carefully. The argon will use it to our advantage and will blow across the build plate to get spatter and other issues off of our build while we're building. So you'll typically set that at the when you do maintenance on your machine and you just leave it. You will see a slight difference if you're doing an aluminum versus if you're doing like an Inconel. But by and large, you set it and you forget it. If you want to really hone in your machine, that's one of the things you could check. Laser spot sizes are typically around 75 microns. That's pretty average. People can adjust those. Not machine to machine. You have to change the F-theta lens that focuses your laser. Your build chamber size or your build plate size is often dictated by the F-theta lens as well, where you see build plates that are 4-inch, 6-inch, 11-inch, and then larger. That 11-inch is kind of the upper threshold of that laser spot size and the F-theta lens where you can't go wider than that. So there's some limits in there, but obviously you can print smaller. It depends on the machine and the manufacturer as to what they do. There's really, again, no wrong answer unless you're trying to push the extremes. If you're trying to go super fast to save money, then you can do a coarse thing where you want a large laser spot size and you're just welding metal. Or if you want really fine details, you could try to find a machine that's 20, 25 micron spot size and doing layer thicknesses that are 5 to 10 microns. But those are extreme in, circumstances that are not the normal. So along with the laser parameters, a lot of the laser parameters are set based on what surface you're working with. So I will set my laser power and my layer, so I know my layer thickness typically, and I'll set my laser power and my scanning speed are the two main ones that I'm going to adjust. And we will typically hatch the contour out and we'll raster around the contour, and then we'll do an infill pattern throughout that part. The upskin is typically a slower laser speed. You're going to not over melt, but you're going to try to have a lower power with a little slower and kind of gloss the top to give you a good shiny surface. The sides, you're really worried about making sure it's a good crisp edge and that you're not bleeding over into the powder that's adjacent to this part. It's because you're carving out your part. And so you'll hone that feature in there. It is easier with a 30 micron laser or layer thickness to have a good contour than something like a 60. And so you'll have, if you want a really good, beautiful part like the showpieces that we see at trade shows, they're typically done at 20 to 30 micron layer thicknesses, and then they just let the build take a lot longer. Downskin, the issue with the downskin is you're trying not to go too high of a power so you can not, because you're starting with nothing below it, or you're starting with supports below it. And so you want to be able to melt into those supports, but you don't want to get all that unfused powder and end up with a really rough bottom surface. The down skin is usually the roughest surface of your part. There's just no good way to get around that, and so you have to keep that in mind while you're designing your part and while you're orienting it on your build to actually build the part. Upskin is typically the best. Infill is we're just getting metal down. So we're typically going at a hotter power, we're going faster, we're trying to save some time because we took the time on the downskin, the sides, the contours, and the upskin. So we're just trying to get things done. Now there are some ways we can mess with this to get better results and to decrease costs. So as I mentioned, layer thickness and your hat spacing kind of plays a big role in this. So what we'll do is sometimes we'll do the contour at 30 micron layers, and then we'll do the infill at something like 60 micron layers or 90 micron layers. And so you're skipping every two layers as you're going up, and that allows you to save time with the laser rastering around. So typically when you're talking to build, the recoating process is usually about 10 seconds on a layer. The lasering, though, while you're lasering, say it's a 11-inch by 11-inch build plate, the lasering could take a couple minutes. We could be talking 4 or 5 minutes per layer. And if you're doing 30 micron layers and you're doing any sort of decently sized build, if it's 10 inches, you're probably talking about 2 weeks' time to get that whole build done. If you make it 60 micron layers, you cut that time in half and you can make it be done in about 5 days. So we're talking massive savings. Well, if I do the contours and I just raster those every other layer, it allows me to save on a lot of that time. So I still spend the 10 seconds for every recoat, but every other layer, instead of being 5 minutes to weld, it's about 30 seconds. And so there's different things you can do. And the machines, when they have the software that comes with the machines, different softwares will allow you to do different things. And some of that is patent-based, and some of that is just based on the programmers who developed everything. Same with the contours. So I have 2 contours up there on the top of that upskin that you can see. When I do the contour, we will sometimes do one as a pre-contour and one as a post-contour. Sometimes we'll do 2 pre-contours. So there's different things you can do. And each machine manufacturer is a little bit different, and they claim theirs is the best. But you need to remember at the end of the day, you're still getting overall good surface finish if you're doing what you're supposed to. And you're still getting a 99% plus dense part. So you're going to have that little bit of wiggle room in there. It's just a matter of, did I save time this way or did I save time that way? I'm really not going to knock a machine here because I've seen them all produce very, very good parts. Nuance comes into that where some of them tend to work better with heavier metals, or some of them tend to work better with lighter metals, so an aluminum versus an Inconel. A lot of that comes down to the recoater that you're using and the powder supplier that you're using as well. So that's more where the nuance comes in. But when it comes to these type of parameters, it's pretty accepted industry-wide. All right, so key points for this is some of this is going to vary widely. Each machine, each material, and each layer thickness is going to have a unique set. And that's dictated by the mechanics of the machine and all the details of how it's built. There's crossover studies where we try to take one setting, one laser parameter setting, and build it on another machine. And that comes with a lot of headache. That goes back into why standards are taking so long and why NIST is having trouble with some of this. If I build a part with one setting on one machine and I do it on another machine, it's not exactly a core laser. It doesn't work. So major OEMs often provide their common material parameters for you with your machine purchase, or they allow you to purchase them from them If you buy a used machine, they will typically ask that you then buy the parameters, because the machine, as you're doing your warranties and all that, they're not going to give away all the stuff for free if you got a used machine at a garage sale or whatever, which I've seen. So that's out there. There's typically 10 or so metals that are produced and well-known. Those are mostly aerospace materials that are developed. Other materials are being developed. All of these machines can be used to develop your own set of parameters. So if you're doing unique metals, or you're doing a very specific type of part and you want to develop something to really hone in your machine, you can use any of these machines for this. Some machines are a little bit easier to work with on the fly than others, but overall, they all do well. They all do very well. The powder supplier does make a significant impact on the machine optimization. Most OEMs will not certify powder that is not supplied by them, which is really frustrating as a machine user, because they will mark it up 2 to 3x and then sell it to you, and you look at them and you're like, you're buying it from LPW or Praxair or Carpenter, and you're remixing it, you're having your own mix, and then you're marking it up 2 to 3x. A lot of that comes back to the fact that their recoder is designed to handle a certain type of thing. Their laser parameters are designed to deal with a certain type of powder. And I've taken one machine supplier's powder, so for example, something like taking a Renishaw and putting an EOS or a 3D Systems in an EOS, or EOS and a 3D Systems, something like that. We've done those, and they don't always work well in the other person's machine. And so it kind of goes in there. Now, nothing is saying you can't just tweak it. You can buy the other large powder line. If you're doing lots of builds, get a good reputable powder supplier. And if you want to certify it yourself, by all means, please do that. You can save a lot of money that way, but you will be doing a couple weeks of studies, if not a couple months of studies, to get this honed in a little bit. But you can start with a lot of things that are out there. So if you're doing aluminum, you already know where you're starting. Laser parameter-wise, you're just tweaking it. All right, so let's go into metal powder, since I've talked about some of those issues. Metal powders, the main objective is a smooth spreading for each layer without clumps or streaks. That's your overall main objective. Depending on what you're doing, that's not always easy. So some of the contributing factors to that is flow tests that we've done and that are standard out there do not equate to spreadability of the powder. The other thing is the recoder type and the speed impacts how it spreads. So a harder recoder can push things a little bit better. A softer recoder will give a little bit more, and so it takes a moment to build up. So a recoder that's hard, you can run sometimes a little slower. The softer ones, you need to get a little bit going. You need a good tumbling motion with the powder as you spread across that layer. Additionally, if the powder is at all moist, or if you have a soft recoder blade, I've seen it clump to the actual recoder blade and drop little clumps on your build as you're working across the layer. This means that when you laser that next section, instead of it being a nice, beautiful 30 micron layer, it could be 100 microns in that spot. And your laser's not designed to go through that, and you're going to end up with a large defect there. Uniformity of the powders really is the best leading factor into how well it spreads. So powders are typically argon gas atomized, nitrogen gas atomized, or water atomized. The best one by far for industry tends to be the argon gas atomized. It gives nice spherical particles. Nitrogen is second to that, but again, the nitrogen can affect the metal depending on what type of material you're working with. Water atomized powder tends to be a lot rougher. It tends to have jagged edges. It's not nearly as uniform. And while it packs really well, it doesn't spread really well. So this is one where the traditional powder metallurgy that's used in traditional machining is good for a lot of these, but for laser powder bed fusion, we need a very specific one. So we use a very small portion of the overall lot that they're creating every time. So the ideal metal powder is going to have a uniform thickness. It's going to be somewhere between 15 and 45 microns in diameter. We usually have 30 as your average. Most layers, as I said, are 30 microns to 60 microns, and so this allows them to be spread. Some suppliers will have more fine particulates in them, and those work better with a harder recoater blade than a softer recoater blade, and some will have larger. So their spreads vary, and this is, again, where it comes in, where the OEM will certify one type of powder and say, I've developed everything for this. That's the only one I certify. You can use another one, but I just won't certify it. Spherical particles, argon gas atomized preferred. Again, you get the recoater going in a good tumbling motion, and it allows you to kind of get a nice smooth layer. Here's some images. So this is a good quality Inconel 718 powder that I worked with and I did some tests on. You can see the nice spherical particles in there. We have a D50 at 32.1 microns, it's about right, a D10 at 18 microns, and a D90 at 49 microns. So slightly high overall, but this was really good powder. It came from a great supplier. We had no issues running this powder on our machine. It was really good. But this is kind of what you're looking for. I believe that this will improve as time goes on. We work with the powder suppliers because they're trying to get this down and give us what we need. So there's a lot of feedback going back and forth right now on this topic. But this is your average. All right, so let's go through some defects. This is that scary section that nobody wants to see, but also the best learning opportunity. These are two builds. You can see their failures. I did both of those builds. Not good to come back in the morning and find those. But we're going to go through some of the macro defects. Those are your big things that happen and go wrong. Those do not happen often. If you're doing what you're supposed to be doing, they should happen very infrequently. I do a lot of laser parameter development. On the right side, we were doing fatigue specimens for some parameter development, which is why they failed. And so we'll talk about the macro defects, then we'll go through the micro defects a little bit. So that fatigue build that I mentioned, here's another one on the right. This one is one that did not fail as bad as the other one. So from the surface, it looked like it was doing great. But now that I pulled it out of the machine, it suddenly looks like it's not doing well. And what was happening is that in this particular build, I was using a soft recoater. I was using silicone. And the silicone would give as the parts would warp. So they delaminated on the edges. I did not support the edges properly. I used too thin of the supports. My goal with this build was to easily remove them, and they removed too easily. So they warped on the edges. And then as they moved up, you can see that they warped side to side a little bit, and that's as the recoater is spreading, it can't smoothly spread that next layer, and so it's accounting for the differences as it goes up. On the top surface, it looked overall like I was doing well, other than you could see on the edges that I was not spreading powder over the next layer each time. On the edges, it was showing that I was seeing bare metal, and that's because it had propped up. It was probably around 100 microns above my layer, and my layer was 60 microns. And so, again, new powder wasn't really spread. Most of these failures, once you have your machine honed in, or if you're doing what's recommended to you, should not be an issue. But, yeah. So the other thing you can see is on the left, this is a catastrophic failure. We were teaching a class, and this is where I let everybody support their own parts, and we saw what happened. So this was a chance for me not to tell them what to do. And they did not support one properly. So you can see the big streak of heaping powder in the middle. A part popped off the plate. It took a gouge out of our recoater, and then it obviously didn't spread layer to layer. In the spot, the laser is still going on, and it's still trying to weld that, so it ended up being a large just chunk of metal. Ended up stopping the recoater in the middle of the build. We came back in the morning and found this where the whole machine had shut down on us. So this is an important lesson because one error will propagate throughout the entire build. Most of the time when your build fails, it fails in two areas. The supports will pop off of the plate from the thermal stresses, or the part will pop off of the supports. Those are the two most common issues that we run into if you're going to have a catastrophic failure. Everything else tends to be quite minor. With these failures, the supports popping off the plate will usually happen within the first hour or so of you starting the build, and the parts popping off the support will happen within the first hour or so after you transition to your parts, because that's when you're building up your heat sink and you're building up some of those internal stresses that are moving back and forth. So you can typically find depending on how quickly you transition from supports to parts, if it's a 3 millimeter gap, so you're using something like a wire EM to cut it back off, 2 hours is about sufficient to watch your build, but you really need to start the build and have someone there to monitor it, especially if you're doing a new type of part, a new support design, any of that, because that really affects it. After that, usually if it's been going good for about 4 or 5 hours, you're safe to go home, come back the next morning. I will try to start my builds around 10 o'clock. So I prep the machine a lot the previous night, so I'll pull the build out, start the turnover with the plan to come back in first thing in the morning and restart it, or I'm passing it off to someone else who's able to watch it, depending on our schedule of the workflow. Another common issue that is less common nowadays, it used to be more common, is powder shorting. This is when you start running out of powder towards the end, so your dose that you put in there is not enough. And so as the part is welded, it tends to shrink down. This means that you need more than the 30 microns. If I'm using a 30 micron layer, I need more than 30 microns to spread, because any part where I had an infill, it's now lower by some amount. So we usually dose at approximately 120 to 200%. That is higher when we're doing the first couple layers. And then there's also the issue that once you put the powder into the machine and you pack it in there in the supply feed, as that raises up and it's pushing against it, if you have a large build, that supply will pack down as well. So while the gears moved up 30 microns, because the powder is packing down as it goes along, you might have only spread 25 microns of actual volume across. So there's nuance in there. We typically go 150 to 200% depending on what I'm doing and how big the part is in the machine. So that is something that adds to your cost. And you need to recognize that if I'm building parts, I have to have enough money to purchase double the amount of powder for the part, depending on what you're doing. It's very hard to get into a new material like titanium without a large deposit because of this reason. If you're building a full build chamber of titanium and you need to purchase $50,000 worth of titanium, but you're getting $20,000 for your part, that initial investment, you need 2 or 3 builds to recoup that cost. A lot of those costs will be passed on to the purchaser, so will upcharge a little bit. But this is a common issue, and if you just know your machine and know how much you're using, you should not have this problem. Thermal distortion, we talked about this a little bit earlier. These are 2 classic examples of a part that is popped off the supports and is therefore failing. So this is also considered a catastrophic failure. This part's not going to move along past this point. We are trying to develop in situ monitoring to spot these as they happen. And that way we can just shut down the build and say stop. It prevents you from using a lot of expensive powder as you're working along. It also prevents the machine from going. It would be nice to be able to get text messages saying, hey, go check your machine because I think it failed. Not there yet, but I think it will come one day. So these are more of the recoder blade defects that you can see. We're going to cover the picture on the left first. You can see where it caught the part, and then so you had some features on that part that are sticking up above the surface instead of down below. And when the recoder came across, it nicked it or it caught it, and it'll either fling powder or it'll scrape it. On the left is usually a soft recoder issue where it'll take a little nick out of the parts or it'll take a little gouge and won't spread smoothly. On the right is typically a harder recoder problem. You can see that little wavy feature in there, and that's the recoder kind of bouncing as it goes along. So it hit something and there was a little bit of reverberation bounce in there. Again, it's causing not a smooth layer. So your ultimate goal is a beautiful smooth layer every time. How you set your parameters, the type of part you're building impacts this as well. For some reason, lattice structures tend to prop up and nice infills tend to go down. And so if you're building lots of lattices, you can impact it with recoder because it's up above the surface that you're planning to build. Laser parameter settings can decrease all of this, but just kind of honing it in. Some more defects, so you can see some more of these on the left, some of the rippling, some on the right, you can see streaks. One thing does impact the other thing. So if you have one, so on the right build, this was a build where we were working on where one streak impacted another streak, which then caused another thing to flick and move, which then that particle got dragged and damaged the recoder blade. And so one error led to another error, which led to another error, and so slowly spread across your whole build plate. A lot of the machines nowadays have a feature in there where you can just turn off a part, where you stop lasering it. And that is overall your best solution. So you'll have a grid of parts, and if you see one that's going wrong, you just say stop, kill that part, and keep going on with your whole build. If you're in a service provider where you're doing lots of different parts on the same build, you want to be able to still complete the build and get most of the parts out the door, but not impact the others. Obviously, in an aerospace environment where we're dealing with extreme quality control issues, any of these defects would be just scrap it from the get-go. Overall, they don't happen as much once you have things honed in. These were largely test coupons or samples, so I'm showing you the bad stuff right now. So let's go into micro defects a little bit. So most of your micro defects are porosity somehow. You're either going to have a keyhole or you're going to have a lack of fusion defect. Balling can happen if you are at all doing what you're supposed to be doing. You should not be getting balling. It's usually when you're going too fast. You tried to go really hot, really fast, and you didn't have the surface tension wasn't right in the melt pool, and it started forming little balls. It's the same thing that happens in welding. Lack of fusion defects, you usually don't have enough laser power. Those are overall the ones we're most concerned with. They tend to account for most of the build failures when we're doing like a tensile test or fatigue test. Keyhole formation does happen. It's usually too hot. Keyhole defects are usually small and they're spherical. And because they're small and they're spherical, we tend to ignore them. And so if you have to error in some sort of way, you typically end up being closer to the keyhole formation zone than the lack of fusion zone because of the type of defect that's caused. This also allows you to, if you have a little bit of a clump on some powder, to laser through it and keep moving. So let's keep going. Your layer thickness, your hatch spacing will be kind of tuned to some of that as well. But again, lack of fusion is what we really don't want. Keyholing we're okay with. If you're having balling, your laser settings are way out of whack. So let's compare these back and forth a little bit. Lack of fusion tends to be the most common cause for concern. It's insufficient laser energy density. It could be due to a clump of powder landing on your build. You could have a dirty lens because you weren't maintaining the machine properly. Spatter particles, spatter tends to be much larger than the layer thickness, so a spatter tends to be, it could be 2 to 5 times your average laser or your layer thickness. And so there are smaller particles in there as well, but some of the larger ones, your laser is not tuned to go through that. Poor hatching strategy, that type of thing can cause lack of fusion. So if your hatch is not overlapping properly, you can have a defect there. Keyholing, again, small spherical pores, they tend to have several in a row. Balling typically don't cover a lot. So I'm going to speed up a little bit. Some of the effects of spatter, I'm going to jump through this because there's some more good stuff on the other side of this. And we're running low on time. But I did a study where we were looking into this. We basically built a bunch of microscopy coupons, and we looked at hitting them with spatter before we recoated or after we recoated, and we used the direction of the R-flow and flow to our advantage. Here is some of the microscopy images from that. The back left is where we had the spatter particles landing on the build plate, and then we would laser that section. And so industry, the accepted industry thing is to laser from the back towards the front, and so, or against your, back to the front as against your argon flow. And that's because when you recoat the next layer, any of those larger particles you tend to brush off, and they tend not to cause a large issue. So you'll see in the other 3 images, we have some small defects, mostly lack of, or keyholing. In the back left, we have a couple lack of fusion. Those are the larger ones. Tensile testing, if you do them the correct way, where you hit it with the spatter, you recoat and then you laser, you have pretty much the same tensile test across the board. So this is what you should do instead of the worst case scenario. So let's go through choosing some of the right parts, and now that you have this background. The quick and dirty approach that I look at is it difficult to machine with the typical CNC? Does it have internal features? And is it low volume? If you can CNC this, part, you really don't want to do this. You really, if I take a week or longer to build one part plus post-processing, why would you do that when you can machine that part in a day? And the answer is you wouldn't. So you start with a large bill of material when you're CNCing and you work down, but if you have internal features, if you have any sort of like internal cooling passageway, then that ends up being impossible to machine, so you're looking at something like additive. Low volume, we do this for a lot of prototyping. I can do several different parts that are prototyped at once on one build tray, and so I can test several different things at once. That's very helpful when you're trying to make a generation or 2 leap in your part design. Some of the other things you need to consider, so DFAM is designed for additive manufacturing, but the other thing you need to look at, so we'll go into this a little bit larger on how you choose a good part. And you're going to look at, can I optimize this part? If I have the freedom to make this part as complex as I want to, then it might be a good candidate for additive manufacturing. If I'm dealing with a reverse engineered part where I need it to be this specific thing, and it's been traditionally manufactured in the past, it may or may not be a good candidate. That depends on how long it takes you to make the traditional way. So the other thing you need to consider is your life cycle creation, which is what we're going to go through next. And that includes heat treatments, post-machining, any tolerances, that type of stuff. So the first section is largely additive. The second section on the bottom is largely what we would do afterwards. That's your post-processing. So the key focus in the first section is how do I plan to support the part so it doesn't fail? And then how do I plan to remove those supports after I've built my part? If I can break away those supports or I can grind them off or some sort of method like that, that's easy. If I already have to put it in a CNC to remove some of those supports, then maybe I want to design my part slightly different so that I can CNC it. Maybe I need to build fixtures on my part that I can then CNC back off. Maybe I won't build my part exactly the way I had looked at. So there's a lot of these steps that are the same in a foundry. So if we're doing a casting or some sort of other type of manufacturing process, there's a lot of these steps that are the same in both, but there's some that are very unique. A stress relief heat treatment step is unique. We typically will do that before we remove the supports, and that way when we cut the supports off, the part doesn't pop and potato chip on us. Then we'll remove it from the build plate, and then we'll remove the supports off of that. If you can build the part directly on the plates, then you don't need supports underneath it, and there's some tricks that we'll go into for some of this. And then the other thing is do I need to do a hot isostatic press, a hip? Do I need to do an additional post-heat treatment, any CNCing? That type of stuff needs to all be considered when you're designing your part. And the main reason is you might be able to build it easier and use less supports if you build it one way, knowing that you're going to do an additional step later on. So here's a nice supported part. You can see this. We grabbed this one from 3dhubs.com from a GE concept laser. So you can see the nice mesh support in there. You can see how they've featured the internal of the ring on top. Most of this was built with a rule of thumb that we use. That's a 45-degree rule. You need to orient your part so you have as minimal supports inside of your part as possible, because it's really hard to get those back out. Any surface that is less than 45 degrees typically needs to be supported. That's your rule of thumb. There are machines that can get around that with certain materials in certain settings, but overall that's kind of your rule of thumb for most of your machines. So while I'm designing my part, while I'm doing a topology optimization on my part, I'm usually considering that 45 rule. So I will build the part trying to get as many things that are steeper than 45s, or I'll orient it such that I can. Allows you to get everything back off easier. All right, so you can remove it with snips, wire EDM, bandsaw, grinding, milling. People are looking at chemical removing. So bandsaw and wire EDM are the most common. You'll have different thicknesses of supports depending on which way you're doing. We're going to skip past some of this because we're running out of time. So really with the post-processing, your goal is to hit your spec. So you're doing your material property enhancement, surface finish control, or dimensional control. So do I need to heat treat my part? Do I need to hip it? So a hip here this is a part with some really terrible porosity in it, but after hip we were able to squeeze a lot of those pores back out, and that greatly aids in your final part. Abrasive flow machining is great if you have internal passageways. This is from some friends at Extrude Home. It allows you to get through a lot of this. So again, 45-degree rule. This is really what you're focusing on. If you're doing an internal passage, consider, instead of making it a round internal passageway all the way through, so like a coolant chamber, consider doing something like a reverse teardrop shape or a diamond to get around those 45 degrees. The other thing you can do is if you're building a hole that you know you have to CNC later, don't build it because it'll make the CNC walk. and so you won't get as good of a hole if you're touching up a previously made hole. And so just make it solid and just touch it up later on. So optimization, so you can see this. I'm going to do this case study real quick. So this is the part I optimized, and we came up with this gorgeous topology optimized drawing that I had to draw by hand in CAD. The thing that comes from that, though, is would I actually do this in real life? And probably not. So yes, the part is lighter. It looks cooler. But the question is, how much lighter is it, and can I hit it from a normal traditional CNC? If I can CNC this part and do a topology optimization in a different way, then I probably want to do that, then do something like laser powder bed fusion. So this comes back to the following the money question, where laser powder bed fusion usually costs 10 to 100 times. The metal powder alone is a lot more costly. If you need the complexity, if you're doing something that is low volume, or you just need several rapid prototypes out the door quickly, those are great. This is a great option for you. There is money to be made here, but you have to just realize that it's more expensive than CNCing it. So if you can do it traditionally, do it traditionally, but consider your low volume thresholds. If you're only building one, it might be cheaper to do laser powder bed fusion. If you're building several, it might not be. So final thoughts, push button laser powder bed fusion does not exist. It takes a while to learn the way to properly support a part. You get extreme design freedom, but it also comes with a lot of work involved. There is money to be made here. Major OEMs like Lockheed Martin, Honeywell, Boeing, Northrop Grumman, those people are starting to certify suppliers, so that is happening now. A lot of times they will give you the build. They will say, here's a supported part that we've already optimized. We want you to print this file on that machine out of this powder. And if you are willing to do that for us, you can be our supplier. So there is money to be made here. It's getting easier for the smaller guys to make money. Machinists overall tend to have the best training to be able to integrate into this workflow. It's not a huge jump mentally for them, but that is, it's coming. There is money, but you need to be wise with it, so don't lose money. All right, so we're going to go through some of the questions, and I see I have one up already, and if you all have more, please feel free to list your questions. But the one I see right now is, since the part is, oops, it just moved on me. All right, hang on. Since the part is covered by powder, how can you make sure there have not been any failures in the first hours of printing? Excellent. So most of your failures will happen when they delaminate. So you will either have a knot, or you'll either have a rough surface on the powder when you spread that next layer. It'll look choppy. You'll have streaks in it. Or you will see that you're not properly coating your parts. If you consistently see as you're doing each new additional layer that you're having bare metal, you're most likely running into a failure. But that's a good question. And there was a question on how to get a copy of this presentation. I believe this presentation will be out there for people to see from MSC Tooling U. Will be putting this out there. Who develops the slicer software? So the OEM will develop it for their machine, and one of that is because they will use their specific contours, their upskin, downskin, that type of thing. They will typically develop the slicer for their machines. Materialized Magics also can produce great supports, and it used to output some individual raster files for the supports. Most of the OEMs are not using that particular output. They're just using the STLs. So that is something you need to be aware of, is you take a CAD part, you then convert it to a mesh, and then you slice it. So you need to make sure you have a good mesh in that conversion. Next question. In interior cavity, So the interior cavity, you're right. I think I may have put my teardrop shape upside down. That was a great question. Now that I'm thinking back there and looking at my slide, you want that angle, that 45, yeah, I put it upside down. You want that 45-degree angle to be on the top so that you can build it, and you want that nice round surface on the bottom. That was a good catch, and then you'll wrap that around. So supports are mostly necessary for joining the part to the build plate. That is correct. It's joining different features. So if you have any outcrop feature that's kind of sticking out there that is less than 45s, you're supporting it, so you're not starting from nothing, which will cause a lot of warpage and a really rough surface. But yes, overall, it is for locking the part onto the build plate, and most of your failures happen when you don't use solid supports and really account for any, if you're doing a thick part where it's going to want to warp on you. What I said is online monitoring and control. So the monitoring for defects in the industry, no one's really monitoring it online yet. They're trying to get there. The hard part we're having is we're trying to spot lack of fusion defects. Everybody seems to be caught up with identifying those. The regular egregious defects that you would see while you're developing a new build file, you typically can spot those within the first couple of hours, and so we don't set a machine to identify those and let you know. We just assume you'll walk back up and check the machine. They're trying to build a complete package before they release it, is really the bottom line. And so next couple of years, I expect some packages to be released. Right now, most of the online monitoring that you would see is you can hook up basically a glorified webcam where you're monitoring the building. You can log in and see the webcam and see how your build's doing. But there's no machine algorithm learning for some of these areas where it spots it and then sends you a text message or lets you know. I do expect people to get those. It just hasn't happened yet. But with all the tech development, it's going to happen. The process is very reliable after first trials. It is. That's one of the reasons why a major OEM will give you a specific build file with a specific pattern and say use this machine. Because they have to certify quality control. The egregious failures I showed you, most of those were trying to cut corners with supports or were just teaching people to mount things. If you want a really reliable part, use a lot of solid supports. You're going to have to get them all back off, but your part's not going to warp on you at all. It's going to lock in. So most people, when I build a part and when some of my colleagues build a part, we will use a combination between mesh supports and solid supports. We will usually never go one or the other. We'll kind of do a combo. Mesh is usually just kind of getting the bottom surface, and the solid ones are just taking care of any thermal warping. But yeah, it's usually very reliable once you have everything locked in. Lack of fusion defects, sensor technology. There's a variety of ones that I've heard about. I've heard some people using ultrasonic. I've read some research on thermal sensors. There's a variety of different things that people are going after. The success is going to be in a combination. It's not going to be one specific sensor. Thermal tends to work well in the fact that you'll see a signature that you can then read if something's going really wrong. The problem with some of this is OEMs are still developing this. So I've seen cameras, but I don't know the software side, so I can't help you with some of that. But I've seen thermal. I've seen X-ray doesn't work well on the overall build. I've seen, but it's great for learning things. probably mostly thermal and optical. Yeah. So we're running out of time. Any last minute questions? This was great. You guys had great questions today. Okay. Well, thank you. How do you account for part shrinkage during production? It depends on how thick of a feature I'm doing and the layer, how much I'm doing an infill over the entire layer. So that's where that 150 to 200%. When in doubt, put too much powder down, because you can never. It doesn't hurt you to fill up the overflow with excess powder, but it hurts you to run out. So if you have to make a mistake, that's the mistake you make. But that's a great question. Okay, I'm going to go ahead and turn it back over to Nora. Thank you all very much. I hope you have a great day. This should be available soon, so you can read back through it. And I know I skipped a couple of slides, but there's more. If you have more questions, feel free to email me. I would be happy to help you out. I do a lot of consulting for small and medium-sized businesses looking to get into this space. So thank you all, and have a great day. Nora?
Thank you again for joining us today. This concludes today's web conference. You may now disconnect.